Welcome back to our Hypercompositional Algebra series. In the previous episode, we learned how to identify subhypergroups and saw why they are important in understanding the internal structure of hypergroups. Today, we move one step further by studying homomorphisms, the maps that preserve the algebraic structure between hypergroups. Homomorphisms allows us to compare different hypergroups, transfer properties from one hyperstructure to another, and ultimately determine when two hypergroups are essentially the same. By the end of this video, you will know what a hypergroup homomorphism, the difference between good and inclusion homomorphism, why the image of a good homomorphism is always a subhypergroup, and finally, what it means for two hypergroups to be isomorphic. Let's get started. Whenever we study algebraic structures, one of the first questions we ask is, how can we compare two different structures? For groups, rings, and vector spaces, the answer is through homomorphisms. Hypergroups are the same. A homomorphism allows us to preserve the hyperoperation while mapping elements from one hypergroup to another. So we are starting here with two hypergroups. H1 is a hypergroup and H2 is a hypergroup. So H1 this is the first hyperoperation for it. And H2, this is the hyperoperation for it. And of course, f is a well-defined function. At this moment, we don't want it to be onto or one-to-one, just we need it to be a function. A homomorphism, or in some books, we call it inclusion homomorphism, if whenever x and y are in H1, the image of it is subset of f of x star fy. Now, if we go back to groups, we have f of x round y, which is an element, is equal to f of x star f of y, which is also an element. Because we are dealing with hypergroups, x round y is a non-empty subset of H. Because of that, we are writing it as subset of f of x star f of y. Now, this homomorphism, to call it good homomorphism, equality should hold. So this one, we should have f of x round y equal f of x star. And finally, if we have a good homomorphism to be an isomorphism, it should be bijective function. It means that it's one-to-one and onto as well. And in this case, we say that the two hypergroups are isomorphic to each other. Let's give a concrete example. Here we have two hypergroups. We have the hypergroup H1 with circ, and we have also H2 with star are hypergroups. We are taking a map from H1 to H2 such that A is mapped to 0, B is mapped to 1, and C is mapped to 2. First of all, f is a well-defined function. We're saying here that it is an inclusion homomorphism. It means that we are saying that f of x round y is subset of f of x star f of y. Of course, to prove it, we need to take all the possible cases for x and y. It means that x and y, they are subset of, they belong to A, B, C. So we'll consider all these cases. We can start with f of A round A. start with the case when x and y are equal to each other. F of x round x. If you look here at the diagonal, f of x round x is the same as f of x. So basically, this one is f of x. Let's compute f of x star f of x. So let's go back. F of x is in H2. So this one basically is also f of x. We have the equality rule, but can we deduce that it is a good homomorphism? Not yet, because we considered only the case when x is equal to y. So now we need to choose the cases or continue the cases when x is not equal to y. If x is not equal to y, we will consider two cases. We will consider the case A with B and A with C when it starts with A, and the case when it starts with B or with C. If you look here, the table is symmetric. It means that no need to consider A with B and B with A because we have this commutativity. So we have only the case F of A with B, F of A with C, and F of B with C. Again, we did not consider B with A or B or C with A or C with B because we have the symmetry in the two tables. So we'll find here f of A round B. What's A round B? A round B is H1. So this one basically is f of H1. And f of H1, because it's well defined, this one is H2. On the right-hand side, we will find f of A star f of B. F of A star f of A, if we look at f of A here, it's given as 0, and f of B is given as 1. So it's 0 star 1. 0 star 1, it is H2. So here we have also equality. Of A round C is the same case. We'll get also equality. Now, let's look at B round C. B round C is equal to B. So it is f of B. And f of B, it's defined as 1. Now we'll find, using another color, f of B star f of C. F of B is given as 1. F of C is given as 2. So 1 star 2. 1 star 2, if you look, also it's 1. So if you look here, the equality holds. It means that it's not only inclusion homomorphism, it is a good homomorphism as well. But of course, every good homomorphism is an inclusion homomorphism, but the inverse or the converse may not be true. Now let's look at this theorem. This is one of the most important results. We're saying here that if F is a good homomorphism, then its image, denoted by image of F, is always a subhypergroup of the image or of K. Why is this important? It tells us that every homomorphism automatically generates a new hypergroup inside the codomain. This theorem is one of the fundamental connections between homomorphisms and subhypergroups. Although the proof is straightforward, as you will see shortly, the idea is extremely powerful and appears repeatedly throughout hypergroup theory. So let's prove this one together. We need to show that image of F is a subhypergroup. And we need to show that it's a subhypergroup of K. So to prove that it's a subhypergroup of K, first of all, image of F is, of course, it's not empty, and it's a subset of K. The second step, what we need to show is that for every Y belong to image of F, Y star image of F is equal to image of F star Y equal to image of F. Now, if Y belongs to image of F, it means that there exists X belong to H such that Y is equal to F of X. So instead of saying Y star image of F, we'll say that it's F of X star image of F is F of A. This is the union of all of them. A belong to H. But we're saying that F is good homomorphism. What does this one mean? It means that this one is F X circ A with A belong to H. Which is F of C such that C belong to X round A. It's all F of C such that C belong to X round A. And this one, of course, it's a subset of image of F. So this one basically is subset of image of F. We proved here that Y star image of F is subset of image of F. Our aim now is to show that image of F is a subset of Y star image of F. How can we do that? Now we'll take an element. So we proved that Y star image of F is a subset of image of F. And here, as if we are proving the binary clause or the closure, our aim now is to show that image of F subset Y star image of F. So we need to take arbitrary element in image of F. Since B is an image of F, it means that we can find A such that B is equal F of A. Our aim is to show that F of A belongs to Y star image of F. This Y is equal to F of X. Instead of this, we write F of X. And this A is in H. So F of A belongs to F of X star image of F, and A belong to H. We need to show that this F of A is in F of X star image of F. So it's enough to show that A, we can write it as, or it belongs to X star something, let's say A prime. This is what we need to show. What do you think about this one? Can we write A as an element in X star A prime? We have AH equal HA equal to H. What do you think? Using this one, can we deduce this? A belongs to H or XH. It means that A is in X star A prime. And we're done with the proof. Here is another example to show that this function is a good homomorphism. I will keep it for you to practice. Take all the cases that we have in the left-hand side. So here we have H1 circ, and here we have H2 star. And if you look at this one, this is the biset hypergroup that we discussed it earlier. So I will keep this one for you to test your understanding on it. A particularly important kind of homomorphism is an isomorphism. An isomorphism is a bijective good homomorphism, as we said before. So when two hypergroups are isomorphic, they may look different, but algebraically they are identical. And every property of one hypergroup can be translated to the other through the isomorphism. Here we'll consider an example on two isomorphic hypergroups. This hypergroup, we discussed it earlier. And today we are seeing that Z, the hypergroup, is isomorphic to Z to the hypergroups of even integers that we have here. So first, we need to start with a map, which is a well-defined function. We'll take f of x is equal to f of 2x. This is a well-defined one. X, if x is an integer, f of x is equal to x. So if x is an integer, 2x, of course, it will be an even integer in 2c. So it's well-defined. Our aim is to show that it is a good homomorphism first. To prove that it's a good homomorphism, all what we need is to show that f of x round y is equal to f of x, and here they are under the same hyperoperation. Because of that, I put it circ. So if you look back, they are under the same hyperoperation. So we'll find first the left-hand side. F of x round y is f of a with a belong to mx plus ny. And of course, x and y are integers. F of a is 2a. So the left-hand side is 2a with a belong to mx plus ny. Let's use the green for the right-hand side. F of x is 2x, and here we have round 2y. This one is equal to, elements in it are of the form b such that b belong to 2x times m prime plus 2y times n prime. So this one is 2a. It means that I can write it as C, with C belong to A, 2mx plus 2ny. Now, if you look at these two ones, they are identical as sets because m and n, or m prime and n prime, they run over the set of integers. So these ones are equal to each other. Now we prove that it is a good homomorphism. What's the next step? The next step is to show that it's bijective. Now, f of x equal to x, definitely it's 1 to 1. And for every even integer, this even integer, we are able to write it as 2x with x belong to z. So also it is 1 to 1. So it's clear that it's bijective. We proved here that it is a good homomorphism. It means that it is isomorphic. This final example demonstrates the isomorphism beautifully. Although the set of even integers appears smaller than the set of all integers, but as hypergroups, they are isomorphic to each other. Let's recap. Today, we introduced hypergroup homomorphisms and explored how they preserve the structure of hypergroups. We learned the definition of good homomorphism, studied inclusion homomorphism, and proved that the image of every good homomorphism forms a subhypergroup, and concluded with an example of an isomorphism between two infinite hypergroups. In the next episode, we'll continue exploring hypercompositional algebra. Thank you for watching, and please don't forget to leave your comments or any clarification that you would like, or any reference that you might find helpful, or you want to consult about it, you need it, just leave them. Leave all your comments in the comments on the YouTube video. And if you're interested, you can follow me on LinkedIn by scanning the QR code. Have a great day, and we'll see you hopefully in the next episode.